Okay, grade 12, let's see if we can't work our way through this question. So it says initially there's 1.5 moles of nitrogen gas and 3.5 moles of hydrogen gas, and we're adding them to a 1 liter container at 700 degrees Celsius. As a result, the equilibrium concentration is now 0.54 molarity of the ammonia. What's the value of the equilibrium constant for this reaction at the given temperature of 700 degrees Celsius? So again, if we look back to those steps in completing ice tables, you'll realize the very first step you should be doing is writing out the balanced chemical equation. So please pause this video and write out the balanced chemical equation represented by that question. Okay, I've assumed now that you have paused it and you have written out your balanced equation. Please triple check. It looks like this. Nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas. And remember, ammonia is NH3, as they tell you in the question, not NH4. NH4 is ammonium, and it's an ion. Okay, next thing we want to do is start our ice table. So I have everything filled in here, but I'm going to reveal it in the order in which we do things. So first of all, you have your ice table. So we're going to start off with I for initial, C for change, and then E for equilibrium. So there's how you should have started your ice table. Now, what I've done here, I have my rice, my balanced chemical reaction. I've just separated the 3 species over here just to make it a little bit neater. So my nitrogen and hydrogen are my reactants, and then my ammonia is my product. So when I look at this question, there's a couple things I want you to note. First of all, they tell us the temperature. We do not need the temperature for our calculations, but it's imperative that you realize that the equilibrium constant will change if the temperature changes. So the fact it's at 700 degrees when they start the reaction and when they finish the reaction is very, very important. If I change that temperature, the equilibrium is going to shift, and you know that because of Le Chatelier's. Now, the next thing I want you to notice is, remember, the ice table has to include concentrations, and what they've given you here are actually amounts. They've given you the amount in moles, but they did tell you the reaction vessel was 1 liter. And you know, to find concentration, you simply take moles and divide it by your volume. So in this case, 1 liter. So this one's kind of a little bit easier for you because the container is 1 liter. Your molarity is going to be the same as your moles. So 1.5 moles divided by 1 liter is 1.5 molarity. So let's see what we can fill in this table. We know initially there's 1.5 molarity of N2. So initially I can put that in under my N2. And I know initially there's 3.5 moles of H2. So I can put initially 3.5 moles of my H2. As a result of equilibrium, the concentration of NH3 became 0.50 molarity. As a result of the reaction, the equilibrium concentration of ammonia became 0.50. Couple of things. First of all, that's the equilibrium concentration. And secondly, they already converted it for you to molarity. So be careful in future questions. I might do the same thing, mix and match amount with concentration. So you have to be careful of that. So 0.50 molarity at equilibrium for NH3. So I'm hoping you realized that's where that value should have gone. Okay, have to talk quick, I'm losing battery power. All right, now remember, we're going to assume for now that the equilibrium is shifting to the right, and so therefore we're losing reactants. So these 2 reactants are going to go down, and the product is going to go up. By how much? Well, remember I told you to look at coefficients. So the coefficient in front of the N2 is 1, so it's down by 1x. The coefficient in front of the H is 3, so we're going to go down by a factor of 3x. Okay, what else? Ammonia is going to go up by a factor of 2x. Now, do they mention ammonia anywhere else other than this 0.54? No, they do not. So therefore we assume that the ammonia present was 0 to begin with. Okay, now to solve for the equilibrium, I'm hoping you can see over here, we start with 0, we add 2x, and we end up with 0.54. So 0 plus 2x equals 0.54. Can we rearrange that to solve for x? Yes, we can. We have 2x equals 0.54, so therefore the value of x must be 0.27. With that value of x of 0.27, I can plug it up in here. 1.5 minus 0.27, 3.5 minus 3 times that 0.27, and that will give me my equilibrium values for N2 and H2. So again, maybe I should add that 1.5 minus 0.27. That's my value for equilibrium for N2. And 3.5 minus 3 times 0.27 is my value for H2, concentration at equilibrium. So that's where I'm going to get those numerical values. And then I simply put them into my KEQ expression. Remember, it's products raised to the second over, because of the coefficient out here of 2, over my reactants. So my N2 has a 1 exponent, my H2 has a 3 exponent, although it's not shown in there, is it? That's a terrible story. Alright, so we're going to put a little itty bitty 3. There we go. Alright, and we'll make that a green color momentarily. Okay, so then we plug that in, and we end up, whoops, and we end up with our final value of KEQ of 0.0122. It's amazing how that 3 magically appeared in the last step. There we go. And again, I will make that nice and pretty before I post it to your notes. Okay, and then just before the camera says goodbye, copy this question down and try this, please. And this is where we will start on Friday, going over this one. I hope to see you at noon, Wednesday today, 1 o'clock I believe it is, for our team meeting. And I will open up a slot on Thursday too if you want to go over the ICE questions with me before Friday.